A very good day. We have already discussed two topics on power station layouts and boiler general constructions. Today we are going to discuss about the boiler water steam circuit and circulation theory, which are very important aspects for steam generating process. The first application of steam for rotating a prime mover was done by Hero during 2000 BC, and the equipment he made is known as Hero's turbine. This is the first conceptual design which was done and paved the way forward for application of steam as a source of heat for rotating a prime mover. During the fast industrial development, shell type boiler came up, and this type of boilers were made up of a shell where water is filled and it is heated from the bottom with some fuel, and as a result of that the water is getting heated and saturated steam can be taken out from the top of the boiler shell. Shell type boilers are actually first generation boiler, and they are basically discarded because of several disadvantages, and these disadvantages are mainly related to area available for heat transfer because of the shell size, and there are more of heat loss across the shell boundary, and there is no insulation surrounding it, and they are more prone to explosion as the shell is directly heated, and there are limitations of capacity of steaming and accommodate the higher pressure functionality of the steaming. So that's why gradually they were discarded from the services. The second generation boilers are fire or smoke tube boilers. Basically, they are made in such a way that fire is passing through the tubes placed within a shell, and as a result there is more of heat transfer, but there is limitations also. The limitations are mainly related to choking of these tubes with the chute, and there is a eventual heat transfer stoppage, and also the steaming rate is not so much high, and pressure raising is also time consuming, and it is also prone to explosions, so naturally we discarded it. The early third generation boilers are water tube boilers where water is passed through tube bundles and placed in such a way that heat is absorbed in the tube and there is more of heat transfer area, but at the same time there are much more losses also in terms of exhaust flue gas which is passing through it. Though there is no choking hazard due to chute inside the tubes, as water is flowing through the tubes and heating is done outside the tube, there is no large shell requirement to hold the water, and in this type of arrangement large capacity steaming arrangement is possible without any difficulty in manufacturing, and it is also found to be safer. So naturally this type of boilers gradually developed further in power and utility systems. The next phase of water tube boiler development is the simple vertical bi-drum water tube boiler, where two drums are connected by bank tubes and it is placed within an encased zone, and firing is done from the bottom in a travelling grate, and feed water is fed in the bottom drum or lower drum, and whatever heat is absorbed in the bank tubes, that is converting the water within the bank tube into steam, and steam is accumulated in the upper drum, and from there saturated steam is taken out. In view of the losses observed with the flue gas and considering the arrangement requirement for minimizing these losses and to get more heating of the water within the system, the feed water line has been diverted from the boiler feed pump through the waste flue gas duct. As a result of that, the concept of economizer developed. As we know, it is actually economizing the fuel cost, reducing the heat loss through the chimneys, and at the same time less evaporator heat transfer area is required, as water enters within the tubular part of the boiler with higher temperature. So steaming capacity naturally increases with same size, and we have savings in fuel and improvement in efficiency. So from there this concept of economizer came up. But there are disadvantages also, and particularly if we talk about the disadvantages in this type of arrangement, it is related to scaling of the tubes, as at the initial stage impurities in the water was quite heavy, so that creates the problem of scaling, internal scaling, sedimentation, and as a result it creates the reduction in the heat transfer rate, and tube metal gets overheated. Beside that, there is non-uniform heating across the metal surface. So gradually there was a thinking how to create a circulation system so that we can separate all the sludge and impurities, as well as there is better steam generation capacity within a small space. Considering these disadvantages of primary phase of economizer development, step by step some modifications were made. The first modification was to connect the economizer outlet to the upper drum, and another connection, that is a tubing is taken out from the upper drum, which is passed through the outside of the furnace and connected to the lower drum, and from the lower drum there is some arrangement of blowdown also to prevent accumulation of sludge or impurities scales that was made. So this is the first concept of circulation that was introduced in the water tube boiler recirculation arrangement. and this is a natural type of arrangement which was made based on the principle of thermosyphonic action, where water column at the tubing outside the furnace and water steam mixture in the bank tubes, the density difference creates the circulation force within the water steam circuit. In the next phase of water tube boiler development, it was observed that the quantity of steam generated by heat absorbed in the bunk tubes and amount of heat wasted is significant, and therefore to minimize this heat waste, the concept of water walling of the furnace came up, and we found that gradually from bite drum we came up with the concept of single drum or steam drum concept, and economizer is placed in the convective pass and water heated in the economizer are taken to the drum, and there is a downcomer from the drum which is taking out the water and passing it through the water wall tubes across the furnace, and again that water steam mixture is returning back to drum, and there is a separation of water from steam, and steam is taken out from the drum. So this way recirculation type boiler developed with water wall furnace. Gradually, to improve the heat content of the steam, superheaters are introduced within the furnace zone and in between the convective and radiant zone of the boiler, and subsequently for large capacity units reheaters are also introduced. Beside that, depending upon the requirement, it was observed that the fuel which was usually used to burn at the bottom of the furnace in a travelling grate, we are not getting complete combustion of this fuel, and there is loss of fuel energy with the ash. Residual energy is not available due to incomplete combustion. So there was a concept of pulverizing the fuel and make it available within the furnace just like a gas. It was introduced. So pulverized fuel fired system gradually developed. So with this arrangement, it was also observed that requirement of oxygen has to be met sufficiently so that combustion can be completed and ensured that complete combustion has taken place for optimum evolving the heat, generation of heat and absorption of heat, transfer of heat within the heat traps. So naturally there is introduction of air preheaters and arrangement of supply of primary airs and secondary airs. In general, primary air is the air which is primarily supplied for drying the pulverized coal and flying the pulverized coal to the burners so that they can participate in the combustion within the furnace. Beside that, this primary air provides sufficient oxygen for initiation of combustion. At least it meets the requirement of stoichiometric quantity of oxygen supply. Side by side, there for excess air requirement to create the turbulence, there is secondary air provision. Hot secondary air is supplied through the wind box. So gradually forced draft system, FD fan system was also incorporated, primary air supply system incorporated, and as well as to evacuate the product of combustion, gaseous product of combustion, the ID fan was introduced, induced draft fan, so that it can take away the generated flue gas. After taking away the heat, that flue gas can be disposed to the atmosphere. So ID fan was introduced, and as a combination of FD fan and ID fan, balanced draft system developed. Beside that, gradually concern of environment evolved, and how to arrest the dust particles and other things from the toxic materials from the flue gas, it came up. So electrostatic precipitators, dust collectors, mechanical dust collectors, fabric filters, and selective catalytic reactors, non-selective catalytic reactors, those are introduced for control of SOx and NOx, and this way the present day boilers are evolved in such a way that they are gradually generating more steam effectively with better heat content, with lesser fuel consumption, and utilizing the heat value available within the fuel. Now we'll see the elevation plan of few modern boilers. First one is the corner fired boiler. As the name suggests, in this type of boilers, firing is done from the corner of the furnace, and across the various elevation the burners are attached in different levels, and they are in unison, they are fired together, and that creates a fire cylinder within the furnace. This one is a downshot firing boiler. As the name suggests, firing is done downwards. They may be U type or W type, and here it is W type. That means from the two ends, two walls, from the top, the firing is done at an angle, and after burning, the total product of combustion is moving upward. So initially it is coming down and then moving upward. So naturally it forms a shape of W. That's why it is called downshot firing. This boiler is having a cyclone furnace with superheat reheat installation, and cyclone burners are fitted at the bottom of the furnace front wall. So this type of arrangements are found particularly with high CV coal, where retention time of the coal particles is more and it requires quicker heat absorption. This one is the elevation plan of 660 megawatt supercritical boiler, which we can find in CPAT NTPC unit. And this type of boilers, the features are very much salient, like opposed firing arrangement, and there is no drum. Of course, there is a steam separator, and unlike subcritical units, there is no drum. Though from the morning to late night we are busy in steam generation process for domestic and other purposes, but for industries, getting the steam generation arrangement for specific conditions, it is a tough challenge in terms of quantity of heat used and how much steam is generated with the heat content, on the same. So naturally, steam generation itself is related to specific temperature and pressure conditions, and conditions of steam generation determines the quality of steam. As I told already, it is related to pressure and temperature, and there is a term which is called critical pressure, and when we are generating steam below the critical pressure, it is called subcritical pressure operation. From atmospheric pressure, or from the atmospheric pressure up to the pressure of 224.6 kg per centimeter square pressure, we have subcritical regime of steam generation, and beyond 224.6 kg per centimeter square, it is supercritical. So naturally, critical point is of boiling is 224.6 kg per centimeter square and 374 degrees centigrade. And what designate the critical point is that when we have the water directly flashes into steam without having the process of latent heat addition. That means we are having instantaneous steam generation. The rate of heat transfer in the boiling process has a very critical role. Particularly, every substance has a heat absorption capacity, and as we know, water is having a very good amount of specific heat content. So naturally, we can pump or add heat sufficiently into the water, but it has to be done sequentially, otherwise there may be trouble. So when we heat water in a vessel or container, if the heat flux which is supplied, that is within the regime of control, then we will find that first bulk of the liquid, they are not receiving the total heat, only the water which is layer which is attached to the container, that is getting heated, and gradually that water is spreading heat in the bulk of the fluid. So in this type of situation, the bulk of the fluid is below the saturation temperature, so there is a spread of heat by conduction. So naturally, this is a process of subcooling, and when we continue to add up heat more, the rate of heat transfer increases. Gradually, there are some fluid, particles, liquid particles getting overheated, which are attaining above the sensible heat gain, and they are receiving the heat available in the vicinity, and with this excess heat receiving the latent heat of vaporization, they turns into tiny vapors, and these tiny vapors again, when try to move up across the bulk of the fluid, they collapses and spread the heat across the bulk of the fluid. So in this way, gradually the entire container fluid gradually attains the temperature of saturation temperature, and after that whatever excess heat is received, that adds up to latent heat of vaporization, and gradually we find the more number of tiny bubbles are coming up, and these tiny bubbles, like nuclei, and they are coming up from the top, and they are collapsing together, and gradually, as if from the top of the surface, they are flashing into steam. So this is the process of nucleate boiling. Now there may be another situation of heat transfer when the vessel is getting extremely overheated, and when we pour liquid into the vessel, so due to high heat availability, the liquid layer which is coming in contact of the vessel immediately turns into steam, and as a result there is a steam blanketing, and this steam blanketing affects the heat transfer and boiling of the bulk of the fluid, because coefficient of heat transfer of steam is less than coefficient of heat transfer of water. So as a result we find that there is a situation where heat is getting accumulated in the vessel, overheating the vessel, but there is no boiling occurring as such as found in nucleate boiling regime, and due to the presence of this film of steam blanket. So this kind of boiling is called film boiling. So with the increase in heat transfer rate, we find the temperature difference between the fluid and the tube metal surface gradually increases, and initially during the subcooling regime the difference is very less, and gradually as we increase the heat transfer, heat flux, so naturally incipient boiling takes place and then nucleate boiling, and if we continue to increase the rate of heat transfer, then after certain time a point is arrived when there is a departure from nucleate boiling. Sometimes it is also referred as DNB point, beyond which the steam bubbles which formed like nuclei, they collected together, they form a steam blanket, and gradually that starts the film boiling, and as a result the actual heat transfer reduces, but tube metal temperature difference may remain high with the bulk of the fluid, and after when the entire fluid again transformed into the vapor phase, again we find there is increase in temperature with the associated increase in heat transfer rate. Therefore, the heat addition in the water in the process of boiling has three distinct phases: sensible heat gain, latent heat addition, and superheat gain. Now, this is specific to a particular pressure. As we change the pressure, naturally the saturation temperature changes, and with the change in saturation temperature, the distribution pattern of amount of sensible heat addition, latent heat addition, and superheat addition changes on the steam quality. So, as we go on increasing the boiler pressure, the latent heat of vaporization requirement reduces and sensible heat gain requirement increases. Let us now try to understand the boiling process from the perspective of process flow configuration. When we are supplying heat and that heat is added into water, and there is a constant flow, naturally the heat addition is taking place at a constant temperature, and gradually with the increase in heat addition there is a change in phase and we get steam, and this steam is flowing out of the process or system, and this is an open system arrangement, thermodynamic open system arrangement. And whenever we have heating arrangement in a closed system, then along with the rise in temperature there is a change in pressure that changes the your saturation temperature. Naturally evaporation varies, so that we will discuss further, but before that let us try to understand the impact of heat addition in terms of steam generation and how it is happening when there is a circulation or flow across the system. There is an open system and there is a closed system. In case of open system, when we go on adding heat, so water coming inside the flow passage, it is receiving the heat and gradually there is rise in temperature, and once the amount of heat received giving the water taking the water in the saturation temperature, gradually latent heat of vaporization is getting added, and as a result gradually some steam bubbles come out and we get continuously steam water mixture in the flow system, and this percentage of steam and percentage of water remaining, that is determined by the heat addition process and rate of change in heat addition. And as we go on increasing the heat addition, naturally dryness fraction of the steam changes and we get more rapidly the steam availability from the system. So as a result, quantity of steam is increasing, but at the same time, if we go on increasing the heat addition at much more rapid rate, then there may be a layering formation of steam blanket across the heat transfer surface, and that will gradually result in a situation of film creation, and this film creation, there we find mist of water vapors are coming within the system and water particles are remaining within a steam space. So that creates film boiling, and film boiling is critical for tube material because there may be eventually higher temperature of the tube metal surface and there may be failure. So we have to see how we arrange the heat addition successively so that tube metal temperature is not getting higher and it is damaging the tube by high temperature oxidation. In this slide, as shown in the table, we are getting the outline of the effect of pressure in change in saturation temperature of water. If you see, saturation temperature at atmospheric pressure is 1 at 1 bar it is 100 degrees centigrade, and as we increase this to 50 bar, saturation temperature comes to 264 degrees centigrade, and latent heat of vaporization requirement it is 1640 kilojoule per kg, and if we go on increasing the pressure to 200 bar, then saturation temperature comes to 366 degrees centigrade, and latent heat of vaporization that is required reduces to 592 kilojoule per kg. So that means we are adding more sensible heat as we go on increasing the pressure, and we are requiring less latent heat. At critical pressure 221 bar or 224.6 kg per centimeter square, saturation temperature is 374 degrees centigrade, and at that point we do not require any latent heat. Water is getting flashed into steam instantaneously. In practical application of Rankine cycle, we take out following modifications to improve the cycle efficiencies. The first one is definitely superheating and reheating, and then next one is increasing the steam supply pressure, and as far as possible we try to optimize the exhaust pressure from the turbine at the pressure at which heat is rejected in the CW system in the condenser. And we have also regenerative feed water heating system to improve the cycle efficiency as well as minimize the losses at the that is generating in the heat rejection. From the construction point of view, to maximize the heat transfer in the boiler, we utilize the insulation at the non-firing side of the furnace so that heat is not getting radiated out of the furnace, and maximum heat is absorbed by water wall tubes as well as other heat traps placed at the top of the boiler. Whether we go for continuous pass of water, or like once through system, or if we arrange with a boiler drum circulation of water. So naturally in both the system, there where in the boiler there is a fixed steam water separation system like in drum, or we have a continuous system. We have to see this critical heat flux is not attained instantaneously, and there is no failure of tubes. At the same time, two approaches are there in the circulation process. There may be natural or thermal circulation, that is created by thermosyphonic action between the water coming down to the downcomer tubes and again moving up to the water walls, and there is a density difference, and this density difference gives the force for circulation. Or there may be a pump spaced in the downcomer bottom location, which will give a forced circulation or pump circulation. But the purpose of circulation is very clear. It actually intends to continuously wet the surface of the water wall tubes and necessitate the heat absorption at a rate which is not detrimental for the tube surfaces. So far we have seen this heat addition in single phase condition and two phase conditions are having different perspectives. when we add heat in water and when we add steam heat to the steam, so naturally these are single phase conditions, and therefore the effect of heat addition is continuously changing the temperature. But when there is a two phase condition heat addition, that means during the addition of latent heat, so naturally there is a change in phase without any change in temperature at the saturation temperature condition. So naturally we find that though in this cycle both point 5 and 6 present in the boiler drum, point 5 represent the saturated water and point 6 represent saturated steam, and in between the passage, that is basically representing the addition of latent heat within the water wall tubes. So as such, this with the increase in pressure, this latent heat addition reduces, and therefore the quicker steam generation is attained. At the same time, there is increased rate of heat transfer. This increased rate of heat transfer is actually dependent on circulation ratio, and more we infuse heat within the steam and water mixture, there is more chance of increase in tube metal temperature. So we have to see that we can continue the addition of latent heat within the domain of nucleate boiling. Whenever we increase the boiler operating pressure from subcritical regime to supercritical, that means above 224.6 kg per centimeter square, so naturally the requirement of latent heat addition is totally removed. So we get just after sensible heat addition, water flushes into steam, and due to this type of situation, there is no two phase condition heat addition. We have single phase water heat addition followed by two phase latent heat addition and again single phase superheat addition. But in case of supercritical, we have single phase water sensible heat addition followed by superheat addition. So this transformation gives the potential of increased rate of heat transfer. At the same time, there is more statutory restrictions related to heat transfer rate, so that tube materials must be strong enough to withstand high temperature oxidation chances, and we have to see that the heat addition is taking place in a phased manner, so that transition from water to steam is smooth. So with the change in operating pressure, there is a massive change in heat transfer process, and we see from subcritical to supercritical that when the evaporator part, heating in the evaporation process, is totally absent in supercritical regime, and naturally the efficiency also increased of the cycle, as there is much more heat available with the steam for giving useful work. Sidewise, it is not that all the supercritical units are starting from the supercritical regime only. All the startup operations are in the subcritical regime. So naturally there is a separating unit, steam water separating unit, even with the subcritical supercritical boilers, and this separating unit continue to separate water steam mixture with a circulation between the evaporator tubes and the water walls, evaporator water walls and the downcomers. So this recirculation continues when we are operating the supercritical units in subcritical regime, and as we go on increasing the pressure, gradually this separating device is bypassed and directly water is getting flashed into steam. So this way we find the implications of circulation exist so long we operate in the subcritical regime of operating pressure. Within the boiler furnace, the different types of heat transfer, if we see, there are three modes of heat transfer: radiation, convection and conduction. But the amount of heat transfer that is taking place due to conduction is very minimal, around 20 to 22%, but remaining 78-80% of the heat is getting transferred either by radiation or convection. In fact, radiation heat transfer is predominant because of this coefficient of heat transfer in the process of radiation is having maximum. So naturally it is more effective in luminous zone of the furnace. In the non-luminous zone, second pass, we have convective heat transfer. Convection is there. Let us now try to understand the process of heat transfer within the boiler furnace and what are the impacts of scaling or your corrosion, fire side or water side corrosions. As you see that within the boiler, when the combustion is taking place, the average temperature which is available is around 1500 degrees centigrade to 1800 degrees centigrade. But when the tubes are receiving the heat, so naturally tube metal temperature comes with the coolant flow. Coolant is water or water steam mixture which is flowing through it. So temperature comes around 400 degrees centigrade. It is outer wall of the tube, and inner wall of the tube may have a temperature around 350 degrees centigrade. So naturally there lies a difference of around 50 degrees centigrade temperature between inner and outer wall of the tubes. And bulk of the fluid, naturally we get a temperature of the bulk of the fluid around 340 degrees centigrade. So you see that how gradually temperature gradient changes in the process of heat transfer, and how that is getting affected differently when some impurities comes in. When there is some scaling due to hardness of water or due to corrosion or due to fire side or water side corrosion, due to the scaling, what is happening, the heat received by the tube surfaces, that are these tube surfaces are not clean, and naturally whatever heat they are receiving, due to the resistance posed by this your scales, so tube metal temperature increases beyond the normal temperature, and we may get instead of 400, the temperature comes out to be 430. Inner side of the tube material, naturally it comes to around 380, and bulk of the fluid again we are getting at 340. So you see there is no change in bulk of the fluid temperature, coolant temperature, but outside tube metal temperature is changing. That is the point of concern, that when water is not water or water steam mixture is not receiving more heat, but tube metal is receiving more heat, and as a result its temperature changing due to scaling resistance given by the scales, and there consequently there may be chance natural circulations are naturally occurring due to thermosiphonic action, and they are basically driven by gravity, and as the density difference is there between the downcomer column of water with the water steam mixture within the water walls, so this density difference that creates the thermal head, and that is moving and circulating this total system, water steam mixture and water, so that movement continues. But you see, this is basically, this natural circulation is basically pressure dependent, and more we go on increasing the boiler operating pressure, the density of water reduces and density of steam increases. So naturally the density difference between the water column within the downcomer and water steam mixture in the water walls, it reduces, and as a result of that we need to have some arrangement to maintain the circulation. Therefore, whenever the operating pressure goes beyond 180 kg per centimeter square, then we need some pumps in the downcomer segment so that we can maintain the circulation in the adequate level, so that heat transfer remains at the same condition. Otherwise, due to change in density difference at higher pressure, the circulation is affected. As a result, there will be more localized heat transfer, and there may be formation of film boiling within the water walls. So that has to be avoided by maintaining proper circulation through a pump. The ratio of the weight of water to the weight of steam in the mixture leaving the heat absorption surfaces is called circulation ratio, and this circulation ratio has significant impact in the amount of heat being added within the water steam mixture with respect to the maximum capacity of heat addition within the system of water steam mixture. So naturally circulation ratio is a critical parameter. So we can conclude that if the circulation number is high, that implies the amount of steam formation is less compared to the amount of water available within the heat transfer area. So naturally, when circulation number is high, there is less chances of scale formation within the water walls, and tube material is having less chance of getting oxidized, and there is more heat absorption within the nucleate boiling regime, and naturally it implies that the size of the heat transfer area is more compared to the requiring critical attaining the critical heat flux regime. So naturally there is less scope of departure from nucleate boiling. But if the circulation number is lower, that means rate of steam formation is higher, and there is less amount of water available to wet the evaporator surfaces. That implies also the evaporator is very compact and rate of heat transfer is high, and there is more chances of occurring departure from nucleate boiling, and scale formation chance in the metals are also increasing with the lower circulation number. Power and utility boilers, with natural circulation we have higher circulation numbers. Generally in industrial boilers we can get 12 to 15 as the circulation number. For utility boilers, low capacity boilers, we can have 7 to 9. In fact, 4 to 7 is actually at present it is visible for 30 megawatt to 75 megawatt units. And when we use 210 megawatts and other assisted circulation system, there we will find that circulation number is 2 to 3. And in once through system like supercritical units, naturally when it is operating in supercritical regime, the circulation number is 1. By circulation number 1, we mean that the amount of steam generated is equal to the amount of water getting inside the system, evaporating system. So naturally circulation number 1. That condition only occurs when there is no circulation across the downcomers, and we have entire water is converting into steam. Now for lower capacity units or up to 500-600 megawatt units which are operating under subcritical regime, we have one thing we have to look into, that is related to distribution of water across the evaporator surfaces uniformly, so that the velocity of fluid in the various flow passages are uniform and heat transfer is not getting differential across the tube surfaces. So to maintain and control the uniform heat transfer across all the water wall tubes, we have orifice fitted in each tube inlet, and through that we maintained uniform velocity of water steam mixture across all the water wall tubes, so that heat transfer is maintained and regulated with circulation ratio, and there is no departure from nucleate boiling. Beside that, we have to take care of in the flow passage, we have to take care of heating in such a way this aspect of crossing the critical heat flux condition never arises, and this flow is entirely within the regime of nucleate boiling, and there is no chance of reaching the DNB. That is the end of briefing on process of circulating water within the boiler and getting steam and movement of water steam control through the circulation process. If you have any queries further, you can contact me in the given